Okay, today we will go through the lead-lag compensation process or compensator design. So a lead-lag compensator is a component in control system that usually improves the frequency response in a feedback and control system. Okay, it's a fundamental building block in classical control theory. And it usually influences the influence disciplines usually varies from robotics, satellite control, laser frequency stabilization, and so on. Okay, so this is a overall module schematic of the lead-lag compensator or any kind of compensators. So this is the plant we need to improve. And this is the overall with the feedback over here. And this is the compensator. It can be either a linear gain compensator or lead-lag compensator or any kind of compensators. Okay. And PID controller or compensator is sub module or say sub class of the lead-lag compensator. Okay. And a lead-lag compensator can usually be represented like this in mathematical model. So we have a zero, we have a pole over here, and in case the absolute value of this zero is a lot smaller than the pole, then this is a lead compensator, which means the phase of the entire system will be bringing forward. Okay, and if the absolute value of zero is a lot larger than the pole or somehow larger than the pole's absolute value, then it is a lag compensator, which means the phase will be bringing backward, okay, or more negative value, okay. And this is the cascading or the combination of lead compensator and the lag compensator. So they can switch the position. You can put the lag compensator ahead of it and lead compensator after the lag compensator. But switching the places, it's like you are cascading the system. So this is the plant, or you can simply put this afterwards. And this is the input, and this is the output. Okay, and this is the feedback. All right, you can put it either here or at the before this connection. Okay, if you put it over here, basically same thing. They are cascading, and the sequence doesn't matter. And the reason to use lead-lag compensator is to improve the frequency response or the impulse response, step response of the system of the plant. Okay, so decrease the overshooting, to speed up the accelerate, or to reduce the rising time, or to reduce the steady state error, and so forth. Okay, and this is the body diagram or body plot of the lead-lag system. So there's a gain margin, there's a phase margin. What you need to do with the lead-lag compensator is to change the phase margin from negative to positive to make the system more stabilized, and to change the gain margins to also can improve the stability of the system as well. Okay, and the lead compensation is something like this, and you can read these in the textbooks as well. Okay, so the experiments we need to do today, first of all, you can go through the appendix, okay, to see how this is basically an example of how lead-lag compensation will actually works in both mathematical modeling and also in circuits modeling. Okay, so we usually use such circuits as either lead-lag, this is the gain compensator, or using including the capacitors to make the lead-lag compensation. So the lead-lag, which indicates the poles and zeros, can be configured by the values of these resistors and capacitors. Okay, and the left side is the passive ones, which leads to usually the output, the gain is smaller than 1, and the right side is using the op-amps, which gives you the gain larger than 1 in most cases. Okay, so if the gain is smaller than 1, then over here 1 over k is larger than 1, which means this R1 is positive. And if you use the right side scenario, it will be a little bit different. Okay. All right. So over here, let's go back over here. Okay. So in my lab, today's experiment is to improve the stability and some features, frequency response or impulse response, step response features of this system. Okay, so first of all, we need to draw the body plot of this system. It's very simple, just the numerator and the denominator, and use the transfer function to plot it out with a stepping response and also the body plot. And then we plot the edge of the closed loop step response, which means this is the input and this is the feedback. Okay, and this is the gain. First of all, we do the gain compensator, and then this is the G. Okay, and this is going back, something like that. So the entire system is the edge. Okay, which is the Y and X. Edge equals to Y over X. Okay, so assume K equals to 1, which means the unity gain feedback system. So you need to do the calculation of edge based on this G. Okay, and then based on this edge, you need to record or calculate the values of this omega C, phi, p, and so on. All right, and then plot. So over here in question 3, we assume k equals to 1, and question 4 is to ask you to give different phase margin and the frequency based on k equals to from 1 to 50, and also 1 over 2, 1 divided by 2, 1 divided by 3, and until 1 divided by 50. Okay, so in total of 100 values of this k, you can find 100 pairs of this, and to observe when the phase margin will give you the proper positive value, so that the system will be stable. Okay, the entire edge will be stable. And obviously, if simply k equals to 1, neither G or this edge will be stable. So we need to find the proper K to make this edge be stable. And also, we need to find another K. We need to find a K not only to make it stable, but also meet these requirements. Okay, the system's specifications. So in here, the steady state error will be smaller than 0.01, and the frequency will be larger than 0.2 rad per second, and the phase margin will be larger than 60 degrees. Okay, and then construct the body plot in correspondence to K, the K you picked over here to meet the requirement, times G. Okay, so this is the K, the gain compensator we're looking for to stabilize the system. And then this is simply just for the gain compensator. And then we look for the Lee-lag compensator. Say R2 equals to 510 ohms. And then according to this K, we need to find this R1, okay, in equation in the appendix. So you can use this equation to find R1. That's for the gain compensator. And then for the Lee-lag compensator, over here, we need to pick the proper C1 and C2, use the figure 7 and figure 8 in the appendix. And similar to the techniques we are using over here, like pick K to arbitrary K from 1 to 50 and also 1 to 1 over 50. And we can also similarly pick C1 and C2 accordingly. Not from 1 to 50, but you can set up a certain range for C1 and C2 and see if you can make a lead-lag compensator to make the system stable and also meet this requirement. And also, when you pick C1 and C2, you can calculate omega 1, omega 2 as here. Okay. You can find omega 1, omega 2, and omega 3, and then find the P1, P2 by using these equations. Okay. And you will have the Z1 and Z2 like this. Alright. And then you have both Z1, Z2, and P1, P2, and then you can have the lead-lag compensator. Alright. Also, you need to examine that the Z1, Z2, and P1, P2 meet the requirements like this. Okay, so the absolute value of P1 is larger than Z1, larger than Z2, and larger than P2. And also, their real part should be at the left side of the real axis. Alright. Oh, of the imaginary axis or the y-axis. Okay. So with the proper picking of C1 and C2, okay, you should be able to find the right lead-lag compensator over here. And then you can build the new edge with the lead-lag compensator equals to the lead-lag compensator times the original G, which is this one over here. And then draw the Bode plot, the step response of this new edge, and repeat 3, okay, to find these values. All right.